Welcome to Lecture 3, where we'll be focusing on the concept of distribution in transportation modeling. Throughout this lecture, we will unpack the methods, challenges, and practical considerations of distributing trips across a network. This is a critical step in the four-step transport model as it determines how travel demand is spread from origins to destinations. In this session, we will start by clarifying some key definitions, especially the difference between trip generation and trip distribution. Then, we'll examine origin-destination, or OD, matrices and explore the main modeling methodologies. These include growth factor models and gravity models. We'll look at how they work, their strengths, and their limitations. We'll also touch on calibration techniques, synthetic alternatives, and some practical considerations. By the end, you should have a well-rounded view of the distribution stage of transport demand modeling. To place distribution into context, remember the four-step travel demand model. We begin with trip generation, then move to distribution, followed by mode choice, and finally, route assignment. Our focus here is step 2. The distribution stage, where the goal is to match trip origins and destinations in order to forecast travel patterns. Let's clarify some important terms. Trip generation and attraction refer to how many trips are produced in a zone and how many are pulled into a zone, respectively. Notice that at this stage, we are not yet concerned with where the trips are going, only how many leave or arrive. To capture the full picture, we use origin-destination matrices. Distribution then steps in to model the decision of where those generated trips will actually go. In other words, it mathematically matches origins with destinations to build an OD matrix for future travel demand. The OD matrix is a fundamental tool. Imagine a table where rows represent the zones from which trips start, and columns represent the zones where trips end. Each cell shows the number of trips between two zones. The diagonal entries reflect trips that stay within the same zone, what we call intrazonal trips. In notation, lowercase letters usually represent observed values from previous studies, while uppercase letters represent future values we want to forecast. Here, you see an example of an OD matrix. Notice how it captures the flow of trips across all zones in the study area, including trips that originate or end in external zones. This framework allows us to test and forecast future demand once we apply the appropriate distribution models. It is, in essence, the bridge between raw trip totals and actual spatial travel patterns. When it comes to modeling trip distribution, there are several methodologies. The simplest is the growth factor model, which uses information from a base OD matrix and projects it into the future. A more sophisticated approach is the gravity model, which incorporates travel costs and accessibility. And there are also alternative approaches, such as intervening opportunities models. Each method differs in complexity, assumptions, and the type of input data required. An important principle in distribution modeling is the use of constraints. The total trips generated from a zone must equal the sum of trips in its row of the OD matrix. Similarly, the total trips attracted to a zone must equal the sum of trips in its column. If both conditions are satisfied, we call it a doubly constrained model. If only one condition is enforced, then it is a singly constrained model. These constraints ensure that the model's outputs are consistent with what we know about trip generation and attraction. Another essential ingredient is the cost element. Trips aren't just random. People choose destinations partly based on how costly it is to get there. Cost can mean distance, travel time, or monetary expense. Often, models use what we call the generalized cost of travel, which combines all these factors into a single measure. This may include travel time in the vehicle, walking to and from stops, waiting time, transfer time, and even parking costs or perceived safety and comfort. Governments usually determine the weights for these components, assuming they remain stable and transferable across contexts. Here, the generalized cost function is expressed mathematically. Each component, whether it's in-vehicle travel time, waiting, walking, transfers, or monetary costs, is given a coefficient that translates it into a common unit, typically money or time. This allows us to compare and aggregate the impacts of different trip attributes. For example, we can ask, is 10 extra minutes of waiting worse than 5 extra minutes of walking? By calibrating these weights, we create a realistic measure of travel impedance between any two zones. Let's begin with the first class of models, the growth factor models. These models assume that we have a base OD matrix from a previous study, and we also have information on how much growth to expect in the future. For instance, we might know that overall trips will increase by 20%, or that specific zones will experience more growth than others. The three variants are uniform growth, which assumes the same growth everywhere, singly constrained models, where growth is applied to either origins or destinations, and doubly constrained models, which account for growth at both ends of the trip. The simplest case is uniform growth. Here, we assume every OD cell in the matrix grows by the same factor. If trips in the entire region are expected to rise by 20%, then each origin-destination pair is simply multiplied by 1.2. While easy to calculate, this approach is rarely realistic, except perhaps for very short-term forecasts. It ignores differences in how zones actually grow and evolve. Now let's look at the singly constrained growth factor model. This method assumes we know the expected growth in trips for either the origins or the destinations, but not both. For example, if we have forecasts of how many shopping trips will be generated in each zone, we can apply an origin-specific growth factor. Alternatively, we could use destination-specific growth factors if we know how attractive each zone will be. The formula is simple. Multiply the base trips in each cell by the growth factor of the relevant zone. Here, we see an example of an origin-constrained growth factor model. Imagine we have information on how much trip generation will increase in certain zones. By applying these factors, we can redistribute the growth across the OD matrix, maintaining the pattern of trips but scaling them according to the new totals for each origin zone. The result of this calculation is a forecasted OD matrix. The structure of trips remains largely the same as the base year, but the numbers reflect the projected growth in origins or destinations. This gives us a quick way to predict future patterns, provided we trust the growth assumptions. A more sophisticated version is the doubly constrained growth factor model. Here, we have information about both the number of trips produced and the number of trips attracted in the future. To balance both sets of constraints, we apply two sets of growth factors, one for origins and one for destinations. The Furness method, introduced in 1965, provides an iterative way to solve this. It uses balancing factors that are updated step by step until both constraints are satisfied and the matrix stabilizes. Here's an example of applying the doubly constrained method. We start by calculating the future trips between zones, then adjust iteratively to make sure the totals match the known growth at both ends. The key rule is always to complete full iterations, first adjusting origins, then adjusting destinations, until the differences from the target values are acceptably small. After just a few iterations, often 3 to 5, the model typically converges to a solution where the differences between the estimated and target totals are less than 1%. This demonstrates the efficiency of the Furness method in balancing OD matrices with double constraints. However, sometimes the method does not converge. This can happen if the base matrix itself is incompatible with the target constraints. For example, if a destination zone can accommodate a maximum of 400 trips, but the origin growth would require 460, the model cannot reconcile the difference. In such cases, no solution exists without adjusting the assumptions. To summarize, Growth factor models are straightforward and easy to apply. They use existing observed matrices and simple growth forecasts, making them accessible for short-term planning. But they also come with serious limitations. They inherit any errors from the base year, and they cannot account for changes in travel costs or policies, such as new roads, pricing, or vehicle technologies. Essentially, they are only as good as the initial data, and therefore best suited for quick projections rather than long-term strategic planning. Now we turn to the gravity models, one of the most widely used approaches in trip distribution. The name comes from their analogy with Newton's law of gravity. Just as physical attraction between two bodies depends on their mass and the distance between them, the number of trips between two zones depends on the size of those zones, their generation and attraction, and the cost or distance separating them. Early attempts by Casey in 1955 showed that trip numbers were inversely related to distance. Over time, more refined formulations were developed, introducing generalized cost functions with parameters that can be calibrated. These functions may be exponential, power-based, or even combined forms. Here we see some examples of cost functions. Typically, cost is expressed in time, but it can also represent distance or monetary values. The exponential function assumes that the probability of making a trip declines smoothly as cost increases. The power function, on the other hand, allows for a sharper drop-off at short distances and a slower decline at longer ones. Choosing the right function is crucial because it shapes how sensitive the model is to travel costs. Similar to the growth factor models, gravity models can be either singly or doubly constrained. The proportionality constant is replaced by balancing factors, AI for origins and BJ for destinations. In a singly constrained version, you enforce either origin totals or destination totals, but not both. In a doubly constrained version, both constraints are applied. Once again, these balancing factors are interdependent, and the solution requires an iterative process. Assume values, calculate, update, and repeat until the totals converge to the target. Here we have an example of applying a gravity model with an exponential cost function. In this case, v equals 0.10. We begin with a cost matrix and apply the function to transform costs into deterrence values. The objective is to produce a forecasted OD matrix that matches the target trip totals while respecting the relationship between costs and flows. The first step is to build a matrix of cost function values. By applying the exponential function to the original costs, we translate raw distances or times into deterrence factors. These factors quantify how attractive or unattractive a trip is based on its generalized cost, and they form the basis of the model's calculations. Next, we start the iterative balancing procedure. In step 1, we assume the destination balancing factors, Bj, are equal to 1. Using this assumption, we calculate the origin balancing factors, Ai, based on the target productions and the deterrence matrix. This begins the process of adjusting the model to satisfy the row totals. Once we have initial values for AE, we can calculate trip flows, TIJ, using the formula. Here, OI is the origin total, DJ is the destination total, and FCIJ is the cost deterrence function. This gives us a first approximation of the OD flows, but they won't yet perfectly satisfy all constraints. This slide shows the resulting matrix after applying the first iteration. As you can see, the flows begin to take shape, but they are not yet aligned with all the target totals. This is why further iterations are necessary. The next step is to update the BJ values using the newly calculated flows, and then cycle back to recalculate AI. The process continues until the differences fall within an acceptable range. Now we move to iteration step 1b. With the AI values fixed from the previous step, we update the BJ balancing factors to make sure that the column totals the attractions, match their targets. This back and forth adjustment between origins and destinations is the essence of the iterative process. After recalculating the BJ factors, we update the trip flows once again. Notice that the flows are now closer to the target totals, but not yet exact. This is completely normal. It takes several iterations for the model to converge to a stable solution that satisfies both origin and destination constraints simultaneously. At this stage, we check whether the model has converged. We compare the estimated totals with the target values and calculate the percentage difference. If the differences are still too large, say more than 1%, then another iteration is required. If the differences are sufficiently small, we can stop. Here, the differences are still above 1%, so we must continue. In step 2a, we again update the AI balancing factors, this time using the improved BJ values from the last round. The procedure is the same as before, but each cycle brings the model closer to equilibrium. The key point here is that convergence is gradual and requires patience, but it will stabilize if the input data are consistent. This slide illustrates how the updated balancing factors generate more accurate flows. For instance, the flow between certain origin and destination zones is now much closer to the target. With each step, the OD matrix is refined and the error margins shrink. Now, in step 2b, we update the BJ factors again. This ensures that the column totals match the targets while keeping the row totals consistent. Essentially, the model is alternating between fixing the rows and fixing the columns until both are satisfied. Here, we see an example calculation from step 2b. The updated flow is now much closer to the desired value, showing how the model corrects itself with each iteration. This is the balancing act that makes Gravity Model so powerful. After several iterations, the differences between estimated and target totals are all less than 1%. This means the model has converged successfully. At this point, we can accept the OD matrix as a realistic forecast of future trip distribution. Gravity models offer several advantages. They are politically relevant because the cost function reflects real-world policy levers such as travel times, fares, or road pricing. They also don't require a prior base matrix, only generalized costs and target totals. But there are drawbacks. They involve many calculations, and they can struggle when matrices are sparse, meaning many OD pairs have zero flows. In such cases, the calibration may become unstable. Finally, let's talk about calibration. A gravity model typically requires two z+1 parameters, where z is the number of zones. The AI and BJ factors are estimated using the Furness method, while the beta parameter in the cost function must be calibrated separately. This can be done by trial and error, or more systematically, using methods like Hyman's iterative approach. Proper calibration is essential to ensure the model reflects observed travel behavior as closely as possible. Beyond the growth factor and gravity models, there are also synthetic models. The gravity model is by far the most widely used, but there are two alternatives worth mentioning. The first is the intervening opportunities model, which orders possible destinations by increasing distance from the origin. The idea is that the choice of destination depends not just on distance, but also on the availability of competing opportunities along the way. The second is the direct demand model, which links demand directly to explanatory variables. In practice, however, intervening opportunities models are rarely used because they are difficult to implement, software support is limited, and they offer little advantage over gravity models. In what follows, I dedicate attention to methodological innovations I realized with my team in distribution modeling. Two areas stand out: improving the quality of OD matrices derived from surveys and developing integrated models that combine trip generation, attraction, and distribution in a single framework. These innovations respond to the limitations we've just seen, particularly the issues of data reliability and model accuracy. Survey data is often the starting point for OD matrices, but the quality of those matrices is not always reliable. Sampling errors, non-response, and observation errors can all distort the results. Therefore, researchers have experimented with ways to improve OD estimates, for example, through calibration techniques or by combining survey data with other sources. Here we see an example. A Monte Carlo experiment using Belgian census data from 2001. This census covered over 10 million residents and recorded their departure and arrival locations for work and school trips by drawing different random samples at rates ranging from 1 in a million to 1 in 1. Researchers could test how sampling rates affect the accuracy of OD matrices. To simplify the analysis, the experiment assumes no response bias, no selection bias, no observation errors, and perfect coverage. In other words, the only source of error is the sampling process itself. This isolates the effect of sample size on the reliability of OD matrices. This diagram summarizes the various potential sources of survey error. On the one hand, there are errors of non-observation, such as coverage bias, non-response bias, or selection bias. On the other, there are observational errors, like interviewer mistakes, respondent misreporting, or instrument design flaws. Together, these errors create uncertainty in OD estimates. The Monte Carlo experiment focuses specifically on sampling error, but in reality, all these factors may come into play. The experiment looked at 3 levels of aggregation: municipality, district, and provincial. At each level, it compared the sampled OD matrices to the true census OD matrix, using error measures such as mean absolute percentage error, or MEPI, and a corrected version called MCAPI. These measures quantify the gap between observed and estimated trip flows across different sampling rates. This slide shows results for the municipality level, where the OD matrix consists of nearly 600 zones. The graph plots the mean absolute percentage error, or MAP, against the sampling rate. Notice how errors are extremely high for small samples, often exceeding several hundred%. Only when the sampling rate increases substantially do the errors begin to drop. This illustrates the difficulty of obtaining reliable estimates at such a detailed spatial scale. Here, we see the results using the corrected measure, MCAPE. This metric filters out noise caused by asymmetry in the data, giving a more stable error estimate. Even so, the errors remain very large for low sampling rates. Again, the conclusion is that at the municipality level, surveys need extremely high coverage to produce reliable OD matrices. Now we move up a level of aggregation. The district level, with 43 zones. The errors here are smaller compared to municipalities, but still substantial at low sampling rates. The general pattern remains the same. Accuracy improves only with much larger samples. The MCAPE results at the district level confirm the same trend. Even after correcting for asymmetry, the errors are significant unless the sample is very large. This highlights a consistent message. The finer the spatial detail, the more data is needed to get trustworthy OD estimates. At the provincial level, with just 11 zones, considering Brussels as a separate province for this case, errors are lower compared to TE district level. However, errors remain substantial. The MCAPE results confirm the same trend. Even after correcting for asymmetry, the errors are significant unless the sample is very large. So, what can we conclude from the Monte Carlo experiment? First, no accurate OD matrices can be directly derived from travel surveys at fine levels of detail. At the municipality level, for instance, even very large samples fail to deliver precise results. Second, only at the provincial level and only when half the population is surveyed do we get an OD matrix of acceptable accuracy. Finally, calibration techniques such as those we discussed earlier are essential for improving the quality of OD estimates derived from surveys. Another important conclusion is that MCAPE, the corrected measure, performs better than traditional MAPE, By filtering away the noise caused by asymmetry, MKP provides a clearer picture of true error levels. This makes it a valuable tool for evaluating OD estimation methods in practice. With this, we close the discussion on survey-based OD matrices and Monte Carlo experiments. The findings highlight the challenges of relying solely on surveys and point us toward more robust approaches that integrate additional data sources and statistical models. This leads us to the next section of the lecture, where we look at a direct modeling approach that combines production, attraction, and distribution in a single framework. The motivation is clear. Existing methods often rely on weak or partial information from travel surveys, and we have just seen how unreliable those can be. A direct model, by contrast, builds directly on census-based OD data, which cover entire populations and therefore offer much stronger foundations. Traditionally, three kinds of approaches have been used. First, travel demand models, which separately model production and attraction, then distribute trips afterward. Second, activity-based models, which use detailed household travel survey data to simulate behavior. And third, link traffic count methods, which treat OD matrices as prior information to constrain traffic assignment. But all of these depend heavily on survey data, with all the limitations we've just discussed. Census data, by contrast, cover the entire population in a study area. This allows us to model OD flows directly without tying the estimation problem to link flows or relying on partial surveys. It also opens the door for statistical methods that can integrate production, attraction, and distribution in one coherent step. The result is both more efficient and potentially more accurate. As an example, this approach was applied to the 2001 Belgian census. The focus was the Flemish region with over 6 million residents. The census provided OD data on work and school trips for a normal weekday across all travel modes. At the municipality level, this gave us a matrix with 308 zones, nearly 95,000 cells. This rich dataset forms the basis for the direct modeling approach. One key feature of OD matrices is their hierarchical structure. For instance, municipalities can be aggregated into cantons, districts, arrondissements, and provinces. Modeling at the municipality level allows results to be naturally extended upward to any higher level. This flexibility makes census-based OD matrices especially useful for both detailed and regional analyses. To make the model work, we combine variables from the OD matrix itself with additional explanatory data. Internal trips, for example, are captured using dummy variables. Other factors include employment ratios, population density, and the length of road networks, all of which influence trip production and attraction. These variables are relatively easy to obtain from transportation institutes and provide a strong foundation for statistical modeling. Two statistical models are considered, the Poisson model and the Poisson-Gamma mixture model, which is also known as the negative binomial model. Both use explanatory variables to predict OD flows, but the negative binomial adds a dispersion parameter that captures over-dispersion in the data. In a Bayesian framework, these models require prior and posterior distributions. Non-informative priors are chosen for the regression parameters, while a gamma prior is used for the dispersion parameter in the negative binomial model. Posterior distributions then combine these priors with the observed census data, allowing us to estimate the most likely values for all parameters. Estimation is carried out using Markov chain Monte Carlo methods, specifically the Metropolis-Hastings algorithm. This algorithm is well suited for problems with large data sets and many parameters. Thousands of iterations are run and posterior draws are kept for inference. The result is a robust statistical picture of the model's parameters, their uncertainty, and their predictive power. Finally, predictions are generated from the hierarchical structure of the negative binomial model. By plugging posterior draws into the predictive distribution, we can simulate OD matrices that reflect both the explanatory variables and the random effects specific to each OD pair. This makes it possible to test different scenarios, such as increases in incoming trips to a city or changes in internal trips within provinces. These predictive scenarios are invaluable for policymaking, as they capture both central tendencies and extreme outcomes. Now, let's look at the results from the direct modeling approach. We'll cover three aspects: posterior inference, goodness of fit, and predictive inference. Together, these give us a complete picture of how well the models perform and how useful they are for forecasting OD flows. From the posterior samples, we can compute any statistic of interest: means, medians, standard deviations, and credible intervals. The results show that the most influential explanatory variables are the employment ratio, population density, and perimeter length of both origin and destination zones. In the negative binomial model, the dispersion parameter is also statistically significant, confirming the presence of over-dispersion in OD flows. When comparing models, the deviance information criterion, or DIC, clearly favors the negative binomial specification. This slide shows the posterior distributions for the regression parameters of the negative binomial model. Most parameters are significant and behave as expected, reinforcing the validity of the explanatory framework. The Bayesian approach not only estimates these effects, but also provides a measure of uncertainty, which is crucial for robust decision-making. To evaluate fit, we use the mean absolute percentage error, or MAPE. At first glance, MAPE values are quite high, around 45%. But this is misleading, because small deviations in very low-valued cells can inflate the error. When we focus on medium and high-valued cells, those greater than 10, 20, or 50 trips, the MAPE drops dramatically to 13, 10, and even 7%. This shows that the model performs much better in areas where trip volumes are significant. Here you can see error distributions across cells. For cells with fewer than 50 trips, the average absolute difference between predicted and observed values is less than 1 trip. This is a strong result. Although the relative error percentage may be large in small cells, the absolute differences are very minor. In practical terms, this means the model captures the larger flows accurately while not being destabilized by very small ones. One of the strengths of the hierarchical negative binomial model is its ability to generate predictive scenarios. For example, we can model strictly incoming trips to Antwerp, total trips across Flanders, or internal trips within each of the 5 Flemish provinces. The hierarchical structure makes it easy to scale predictions up or down, from municipalities to provinces. These scenarios provide both conservative estimates, like mean or median values, and extreme cases, such as the 99th percentile, giving planners a full spectrum of possibilities. To conclude, the direct production, attraction, and distribution model offers several advantages. It integrates the 3 steps of trip modeling into one coherent framework. It relies on census data rather than partial surveys, ensuring stronger foundations. The negative binomial specification is particularly well suited, as it captures the over-dispersion in OD flows. And importantly, the model provides accurate predictions for medium and high trip volumes, while keeping errors in small cells within acceptable bounds. Overall, this approach represents a promising alternative to traditional travel demand models. By making full use of census data and by embedding distribution within a robust statistical framework, it addresses many of the weaknesses of survey-based methods. For policymakers, the ability to generate predictive scenarios at different levels of aggregation means more reliable planning and better informed decisions. With that, we wrap up our exploration of distribution modeling in transportation. See you next week.